So this one, we've got a curve y is equal to e, and the area between that curve, the line y is equal to e and x is equal to 1 on the y-axis, is rotated around the line x is equal to 1. So a little bit different this time. So what we've got to, again, work out, well, it's going to be delta x, because it's parallel to the axis of rotation there. So that's why it's going to be delta x there. We can see that. Now, our radius this time, well, it's not from the x-axis. So if that's the point where we've got x, then this is going to be a radius of 1 minus x. And our difference there is going to be in our height. So it's just going to be e minus e to the x, because that's going to be our difference there. So it's going to allow us to get our expression for the area as 2 pi 1 minus x is, and 1 minus x was our radius, so that gives us our circumference, which is the same as our length there, and the height was the difference from e minus e to the x. We substitute that in, we got delta x, so that's okay, and so we expand it out to get e minus ex plus e x e to the minus e to the x, and we got to integrate that between 0 and 1, because that was the limits of the integration. This one's just a little bit trickier, because when we integrate this one, well, all these ones integrate pretty easily. X, e, because that's constant, so it's e to the x, e to the x squared over 2, e to the x integrates to e to the x. But this part, we're going to have to integrate by parts, so we're bringing in those integration techniques. So there's our integration by parts as we go through. We leave these ones, and then we'll throw them in when we're ready to throw all our numbers in. So just be careful with the expressions there when you substitute them in, and we get down to 2 pi outside of 2 minus e on 2. Question 12, we've got the base of the solid being an ellipse, a with a squared, b squared, there, and everything's a square. All our cross sections are squares this time, perpendicular to the x-axis. So again, delta x. But our base there is 2y, so our height would be 2y. So our area would be 4y squared. So 4y squared delta x becomes 4b squared outside of 1 minus x squared on a squared. That's what y squared is going to be equal to. Remember, b squared and a squared are just constants, so we're already just integrating that part there. Between 0 and a, and we're going to take 2, it's negative a to a, so 2 lots of a to 0 to a. Yeah, constant there, go out the front, so we get the 8b squared on a squared times the x cubed on 3 between 0 and a, do our substitution, comes down to the integral that we want. Another one like we had before, where we've got our concrete beam, and it's 15 metres, has plain sides, and the cross sections are rectangular. It's 4 by 3 at one end, 8 by 6 at the other end. So we're able to set up our diagrams like we did before and get our ratios of our similar triangles. So we set up our P and Q cross section, and it's time we're told it's x meters from the smaller end, so that's x there. So sorry, x on 15, P minus 4, but we're getting P in terms of x, so just be careful of what we're doing there. And we do the same thing here with x 3 there, because it's 3 at the small end, so we keep cutting off with those parallelogram. So the x on 15 is equal to q minus 3 over 3, and we get q as that expression. And obviously we've changed it as we've gone through, and we're going to expand out to make sure we get our correct area, which we're then going to integrate between 0 and 15. And we should get down to 420. So we've done some changes, we've made some errors as we've gone through, but check that carefully. And it's pretty similar to what we've done before. This time we've got a sandstone cap on the corner of a fence, and it's in the shape of two intersecting parabolic cylinders. So imagine a parabolic solid, like prism going through, and they intersect there. On the front face, the equation here is 4 minus x squared. So we'll take on about z-axis here, so it's 4 minus x squared, so minus 2 to 2 there, so a distance of 4 across there, and x is the horizontal distance measured from the midpoint of the base of the front face, and z is the height. Okay, the shape of the horizontal slice is thickness dz. So we're taking out thicknesses of dz there, and is also shown. So you get this. So that's what you take a slice through any point, and that's what it's going to look like. So we've got, basically it's a square with 4 smaller corners removed, and so obviously you're going to get some symmetry there. So find x in terms of z. Well, we can get x as plus or minus the square root of 4 minus z. Then we want to show the volume is equal to this. So what we need to do is get our cross-sectional area. So our area there is 4 by 4. So if we find this area we need, we take our 4 by 4 and subtract these positions there. So we know that this point here is going to be x on either side. So that's where we get 2x, because we go across x where the parabola hits. So any point there across x up y, or up z in that case. So we're getting 2x there, so that means if that's x there, it's 2 minus x there. So our full area of a one square there is 2 minus x all squared, which gives us 4 lots of 2 minus x all squared, which gives us this expression here. So that's where that one is coming from. We're going to, x we know is equal to, from there, x was equal to the square root of 4 minus z. So we're able to do that substitution there for x's square root of 4 minus z there. And that's where we get our area, dz. So there's our expression there. There's another way to do it as well when they do some manipulation. So there's our, show that the volume can be given by that, and then hence find the volume. So if we manipulate it a bit, oh, we've gone the wrong way. If we manipulate it a bit there, we expand that out and play with it. Or we can look at it and get this situation. We get 16, 4 minus z all power of a half, minus 16 plus 4, lots of z, and then we can integrate each separate function between 0 to 4, do our calculation there, and we get 160 over 3 as our answer. So check that expansion. Because you're 16, you get the minus 8, right, plus 4, lots of that. So we're just making sure we get that correct and get our answers correct there. But again, once we get our area, we can get our volume from the area pretty easily. It's getting that area correct, and that's one of the harder ones we've seen. But again, if we follow what we've got and get our manipulations and our relationships between our variables, then it's not too, it can be reasonably easy. We say that, but a lot of times it can be hard too. So just be careful, get that correct area, and hopefully if you get the area correct, then the volume will pretty much follow on every time.